Welcome to the 9th lecture from chapter number 7. We are studying VLSI design, and this lecture will study speed versus area trade-off. Speed means it's obvious, it's speed. Area means area or the size of transistors on a given CMOS based circuit. Therefore, area means the aspect ratio. Larger area means larger aspect ratio, right? So we'll see that either we can have good speed, but if you want to have a good speed of your circuit, you have to increase the area. That is a disadvantage because it consumes more space on your IC. And if you want to have smaller ICs, you have to sacrifice speed. So it's a trade-off between speed and the aspect ratio or the area of transistors, right? We'll study the case of CMOS not here, where this is the equivalent circuit of a CMOS not, where this MP, the PMOS transistor, has a resistance RP and a drain capacitance CP. The NMOS has an equivalent resistance RN and a drain capacitance Cn, and Cl is the capacitance of the load the CMOS not is driving at its output, right? In our previous lectures, we studied that Cout can be written as Cp plus Cn plus Cl. We can add, since all these capacitors are in parallel, we can add them and can assign them a single name Cout, or in other words, we can assign a term CFET to this sum, Cp plus Cn, the drain capacitance for PMOS and the drain capacitance of NMOS. Their sum can also be referred to as CFET plus Cl. And there's a small recap. We studied the rise time delay and we derived this expression is 2.2 times Rp times Cout. This Cout can be broken in this CFET plus Cl. So we have broken this Cout into its equivalent CFET plus Cl, and now we have multiplied this 2.2 Rp to this and to Cl, right? And now we are going to assign to the names 2.2 times Rp. We are going to assign it a name 2.2 Rp CFET. This whole we are going to assign it a name TR0, and 2.2 Rp we are going to assign it another name alpha P. Why are we going to do it? Because we are soon going to establish that this is the equation of a straight line. Wow, this TR is an equation of a straight line. How? TR is 2.2 times Rp times CFET. We are going to assign it a name TR0. It remains constant. It doesn't change as we change the load capacitance. 2.2 Rp is alpha P times Cl, right? So now it seems to be an equation of a straight line, because we know that an equation of a straight line is something like this. We studied in school. This m is the slope and c is y-intercept, right? So here we have Cl instead of x, instead of m we have C alpha P, and instead of C we have TR0. So this equation maps on the equation of a straight line we studied in school, right? So let's move on and see whether we can plot it. Yes, not T, but versus Cl. Cl is the independent variable, and can be plotted? Yes, we can. TR, what would be this? This is y-intercept, we know this is TR0. This value is TR0, and we see that as the Cl, the load capacitance, increases, the delay TR increases with slope alpha P. So this is how we can draw it. Similarly, we can derive a similar expression for TF, where TF is 2.2 Rn Cout. This is Rn. We can replace Cout with CFET plus Cl. So Rn CFET 2.2 Rn Cl. So this 2.2 Rn CFET should be given a name TF0. and 2.2 RNCL should be given a name alpha n. So we can write df as df0 plus alpha n CL, right? And we can plot the same df0 on the same, we can plot even this line on the same scale. So if we plot df, that would be somewhat like this, df0 alpha n, and now we have two straight lines plotted on the same plot, right? So this is what we can obtain from, this is what we can obtain by rewriting the already known expressions for TR and TF, right? We already know that Rn and Rp are inversely proportional to, since this alpha p and alpha n, this is a constant, and alpha p and alpha n, which are the slopes, can be written as alpha n is 2.2 times Rn and alpha p is 2.2 times Rp. This means that Tf and Tr is proportional to alpha n and Tf is proportional to alpha n and Tr is proportional to alpha p. Since alpha p is proportional to Rp and alpha n is proportional to Rn, so we can write it like this. The delays are proportional to Rp's and Rn's, and we know that Rp is 1 over beta p VDT minus VTP, and Rn is 1 over beta n VDT minus VTN. This means that Rp and Rn are inversely proportional to their betas, respective betas. So therefore, we can also write it like this. The Tr and Tf, they are directly proportional, they are inversely proportional to betas, right? And betas are, the beta p and beta n are directly proportional to the aspect ratios. We know beta p is kappa b, aspect ratio of p, and beta n is kappa n, aspect ratio of n. This means that Tr is inversely proportional to aspect ratio of p, and Tn is inversely proportional to aspect ratio of n. So what does this mean? This takes us to the conclusion that Tr, if you want to increase Tr, if you want to decrease Tr, for example, because delays are unnecessary, or these are undesirable, we want to decrease them. So if you want to decrease Tr, it's inversely proportional. This means we have to increase the aspect ratio of PMOS. And if you want to decrease Tf, we have to increase the aspect ratio of the NMOS. So delays are, in general, delays are inversely proportional to the aspect ratios or sizes, or the sizes of transistors. If you want to increase, if you want to decrease delays, you have to increase the size. But increasing the size, what's the disadvantage? Because increasing the size, but that's a disadvantage, increasing aspect ratios. Increasing aspect ratios consumes useful space on the IC. So this is a disadvantage. So this is a disadvantage. Increasing aspect ratio is a disadvantage. If you want to decrease delay, we have to increase aspect ratio or the size. But increasing aspect ratio or size, it consumes more space, which is again not good. So there is a trade-off. You can obtain either good delays, or you can either obtain smaller delays, or you can have smaller ICs. But if you want to have smaller delays, you have to have larger sizes of transistors. So therefore it's a trade-off. Right, that's all for this lecture. We will continue studying more about CMOS ICs in the next lecture. Thank you.